Hey, George. It's a monster cat.
Good afternoon, sir.
I pick him up to make him annoyed with me so he'll leave me alone. Seeing the little one start trying to get my attention and okay, cat. Come here. Oh. Also, we're waiting for things to settle in. Anybody got questions about anything, homework or anything? Yeah, I got enough. Oh my God. Okay. Oh, ow, 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 ow. Let me see. 2014. I remember how many people this class has in it. Okay. So we should have. Oh, now everybody's jumping in. Okay. Oh. Oops, that's not the button I wanted. There we go with that. And then we go with this. Need the last little bit. Here we go. All right, we got most people in the class. We're missing 2 people now. If you haven't already done so, please put your name in the chat window. Had a couple of people not do that today. Fortunately, I noticed that they were in class. One of them had answered some of my questions and brought up some questions, and so I knew he was in the class, but he didn't sign in the chat. I must send him a strongly worded letter. Okay. All right. Any questions about anything? Asked that a couple of times, but always good to ask again. Anything about MyLab or any other work? Oops. Click the wrong button there. So we're gonna move on. And first thing I need to do is bring that back down. So when I share the screen, my chat window disappears. So I have to reopen it. All right. In this section, we're going to talk about properties of functions. And amongst those are whether a function is even or odd or neither. Functions come in, there are many different properties of functions. One of the properties is that a function could either be even or odd. And we can determine that from their graph. We can determine that from the equation, the formula. And so that's what we're going to be looking at. But not all functions are either even or odd. Some are neither. So we look at what happens with those. Use the graph to determine where a function is increasing, decreasing, or constant. I think that's pretty straightforward and pretty easy to tell whether a function is increasing or decreasing. I have some disagreements on the notations that the textbook uses. I've discussed it with a few of my colleagues, and they agree that the textbook is wrong. But we have to use their notation because that's what they're using in MyLab. And then we're going to use the graph of a function to locate any local maximums or local minima. Maxima and minima is the plural of maximum and minimum. I don't know why they insist on using the Latin plural form of these words, but they have. That's, I don't know. There's another word here. They're extremes. So they're also known as, sometimes you'll see this word extrema, which is plural for extreme. And so you have the extreme values And so a maximum and a minimum are extreme values, so they're called extrema when we're talking about those two things. Okay, and then we can use a graph to locate those. And we also can talk about absolute maximum and absolute minimum. We'll talk about what that means. A local maximum is different than an absolute maximum. An absolute, a maximum can be both a local maximum and an absolute maximum. But an absolute maximum is not necessarily a local maximum as well. And we'll discuss why. And then using a graphing, so this is, yeah. I'll just kind of read through that. I don't test over using the calculator to find these things. So, but they'll ask you in MyLab. And then find the average rate of change of a function. And if you remember how to find slope, then this shouldn't be any difficulty for you. All right, to determine if a function is even or odd. And there's a third choice here, which they don't ever say. A function is said to be even if for every number x in the domain, the number negative x is also in the domain, and f of x and f of negative x give us the same y value. Right? So f of negative x will equal f of x. So that's what's true with even functions. It is also the word and then and. Oh, they're talking about that there. Okay. So x and negative x are in the domain. So if negative 17 is in the domain, then 17 is in the domain. If 237 is in the domain, then a negative 237 is in the domain. And f of negative 17 will equal f of 17. And f of 237 will equal f of a negative 237. Now, something that results from this, once you start graphing it, and you can kind of see it there in that graph, is that there it's going to be symmetric with respect to the y-axis, but we'll get back to that. Now, for an odd function, if for every number x is in the domain, the number negative x is also in the domain. So it's the same situation here that we talked about with the even functions. However, the equation is different. So this was for even. For odd, f of negative x will be the negative of f of x. So if negative 17 is in the domain, then f of negative 17 will equal the negative of f of 17. So with an odd function, the y values they get, they'll be opposites. Right? So the opposites are in the domain, and the function at those values will give you opposite numbers. Positive and negative of the same number. If it's even, opposites are in the domain, but when you take the function of those two numbers, you'll get the exact same number back. So they'll give you the same value back for those two different numbers. And so this is an example of what an odd function would look like. And and they have symmetry also, but it's going to be symmetric with respect to the origin. So if we took this and we rotated this 180 degrees, the graph would just line up perfectly with itself. So that's called rotational symmetry of 180 degrees. All right, a function is even if and only if its graph is symmetric with respect to the y-axis. And a function is odd if and only if it is symmetric with respect to the origin. So what the if and only if means in these two statements is, man, it goes both ways. So if you have a function that is even, then you know it's going to be symmetric with respect to the y-axis. And if you have the graph of a function that is symmetric with respect to the y-axis, then you know it is an even function. So if we look at x squared, if you remember from algebra, it is symmetric with respect to the y-axis, right? So this point here and this point here, they're mirror images of each other. That means they're the same distance from the y-axis. And if you think about it, -2 and 2 are in the domain, and f of -2 is the same as f of +2, which is 4. They both equal 4. So that makes it an even function. Those two aspects of it, the fact that f of -x equals f of x, and the fact that it's symmetric to the y-axis makes it an even function. All right, with an odd function, if you know it's an odd function, then you know it's going to be symmetric with respect to the origin. And if you see the graph of a function and you see that it's symmetric with respect to the origin, then you know it's an odd function. Corresponding points will be the same distance from the origin. Here, with an even function, corresponding points are the same distance from the y-axis. Now, this graph here is not symmetric with respect to the y-axis. It's symmetric with respect to the x-axis, and it's not symmetric with respect to the origin. If I flip this 180 degrees, I don't get the exact same graph back. So it's neither even or odd. First of all, this isn't a function. Technically, it's a function in the y and not in the x, but for our purposes, it's not a function. It's not an even or odd function. Letter B. All right, being symmetric with respect to the y-axis. I remember teaching my high schoolers, and I remember being taught this when I was in high school, that if you fold it along the y-axis, the two arms will line up with each other perfectly. And so that's what happens here on B. So we look at we look at these values here going straight across. These are mirrored pairs, and so they're the same distance from the y-axis. These high points here, they're the same distance from the y-axis. So any pair of points you take that are corresponding points to each other, then we have a function that is symmetric with respect to the y-axis, and so it's an even function. All right, this one over here, however, all right, if we pick a point down here and its corresponding point over here, and we connect them, the line that connects them will go through the origin. Every single point that has a corresponding point over here will go through the y-axis. Will go through the origin. And they're going to be equidistant from each other. Another thing that happens here with odd functions, if x, y is on the graph, then negative x, negative y is on the graph. And that's what's happening here on letter C. Okay. With even functions, if you have that situation where you have x and y are on the graph of the function, then negative x, y is also on the graph. So that's something to be to think about. Now, to identify even or odd functions from an equation. Okay, so for it to be even, we have to have f of negative x needs to equal f of x. So if I put negative x in the function, I'll get the exact, and I simplify the function, I'll get the same function back. I'll get the original function. And if I put f of negative x, if I put negative x into an odd function, I'll get the negative of f of x. So in other words, every single sign will change. If it was plus, it becomes minus. If it was positive, it became negative. It's very important. Everything, all the signs change. So for it to be an even function, none of the signs will change. And for it to be an odd function, all of the signs change. So if you have a situation where some of the signs changed, but not all of them, then you have a neither. So letter A, with f of x equals the absolute value of x minus 2. Yep. Well, if I do f of negative x, that'll give me the, I keep doing that, the absolute value of a negative x minus 2. And in here, I can factor out a negative sign out of these two, but it's still inside the absolute value. So it's the negative of x plus 2. And the absolute value of a negative is the absolute value of the positive. And that is not good. I don't like that. I don't like it when it does that. I do not. I do not. So this is going to be the absolute value of x plus 2, which does not equal f of x And it also does not equal the negative of f of x. So just by putting negative x in for x, I can look and see what happens. Does it change all the signs, or does it change only some of the signs? Or does it change none of the signs? Well, this one, because we worked through it, it changed one sign. Right? It went from x minus 2 to x plus 2, and we're done. So it's neither. Now, both of the signs had changed inside that absolute value symbol, then it would have been odd. But since neither sign changed, since only one sign changed, not the other one, then it's neither. And let me write down letter. That was A and G. B, we have g of x equals 2 times x to the third. Oh, that's squared. I'm sorry. So I wrote a 3 again. So when I look through my far vision part of my glasses, everything gets double lines. Okay, and so now I want to do g of negative x, which means in place of x, I'm going to put negative x. What I'm doing to x, I'm squaring it. So I'm going to square negative x, and then I multiply it by 2. All right, so the first thing I want to do is square the negative x. What happens when you square a negative number? What happens to the sign?
Does it become positive?
It becomes positive. So this becomes 2 times x squared. So the negative sign disappears because we multiplied it by itself. Plus 3. Well, isn't that g of x? So that made this function even. They didn't show how you get from here to here, but we did. And to break this part down here even further, we get -1 times x plus 2. And if you're taking the absolute value of a product, you can say it's the product of the absolute values of the factors. So I have -1 is a factor, so I'm going to take the absolute value of that, and x plus 2 is a factor, so I take the absolute value of that, and the absolute value of -1 is +1. So that's how we wind up with this. I should have explained that earlier. So it does not equal f of x. And the negative of f of x is the negative of the absolute value of x minus 2, which does not look like this one over here. So that's why it wasn't odd. So the graph is not symmetric with respect to the x-axis or the origin, and the function is neither even nor odd. And so they worked this one through the same way I did and got that it was an even function. So it's just a matter of putting the negative x, replacing the x with a negative x, and doing and then simplifying it appropriately. Okay. When you, all right, and so there's something here I need to talk about. So if you have a negative x to the third power, well, that's just a negative x to the third. Because when you cube a negative number, you get a negative number. So a negative 3 cubed is negative 27, because that's a negative 3 times a negative 3 times a negative 3. All right, these two become positive, then I multiply by negative again, which makes it negative. I'm multiplying 3 negatives together. You multiply an odd number of negatives together, you get a negative number. When you multiply an even number of negative numbers together, you get a positive number. It's just when it's an odd number, you have that negative sign, that odd negative sign out. So these two went to positive. So, excuse me, these two went to positive. So this one is negative. All right. And now we talk about where a function is increasing and decreasing and constant. Yeah. Increasing means where it goes up. Decreasing means where it goes down. Constant means where it's horizontal. Pretty simple concepts. Boom. So we have this function. And we have, let me do it this way. We have these points, -2, right? And -4, and 0, 2, and 2, 0, 3, -2, and 4. And now I'm going to draw a line through those. So this is, that's just going to go like that. And then it goes like that. And then it's a curve from this point on, not a straight line. So it curves down like this. No, it doesn't go through, it stops. Sorry. I'm so used to making points go through. So this was -4, and this was -2, and this is 2, and this is 4, and this is -2, and this is +2. Now, to determine what values of x for which the function is increasing, where is it decreasing, where is it constant? Now, I look at these three things, and I just look at them. I go through and I look I just look at my graph, and I look at my intervals as I look at my graph. So from -4 to positive to -2, it's all one value. All the y values are 0 along there. So it's constant. Every x value gives me the exact same y value on that interval, so that on that interval it is constant. So from -4 to -2, this interval, and we say they're going to say it's closed. Technically, I would say it's open. And most of my every colleague I've asked about it so far agrees with me. but the textbook is going to say that it's going to be a closed interval. But this is wrong. They're wrong. Okay. Now, the next interval here, so it's constant. My next interval is from -2, and we're looking at the x values from -2 to 0. From -2 to 0, all the y values are going up. So from -2 to 0, everything is going up, so it's increasing. And they're going to want you to put them all together, and so they're going to use brackets instead of the parentheses. They're going to include the endpoints. Technically, you don't include the endpoints when you're talking about increasing or decreasing or constant intervals. And then another interval where it's increasing is from 3 to 4. From 3 to 4, the y values are going up. Just like from 2 to 0, the y values were going up. So they would say 2, I would say 2 to 4, I mean 2 to 3, sorry. No, 3 to 4, sorry. 3 to 4, it's also increasing, but they would use the brackets again, 3, 4. So what I want you to realize is that although you're supposed to use the brackets in MyLab, it's wrong. You're supposed to use parentheses. But if you use parentheses, they'll tell you it's wrong. And I don't want you to be counted wrong, even though it's correct. Can you tell it really bugs me? I've been teaching out of this guy's textbooks for ever since I started. So this is 3 years now. Probably, no, I've only used Sullivan books since I started teaching at PAC. And it's the only textbook that does this. And Sullivan should know better because he's written dozens and dozens of math textbooks over a couple of decades. So that covered those intervals. The only interval left is from 0 to 3. Notice I skipped this 2 here. All right, because the y values don't change direction. So they just put a dot there. It has nothing to do with these intervals because the y values are still going down. So we just include that in the interval from 0 to 3. From 0 to 3, or as they would say, the closed interval from 0 to 3, the y values are decreasing. Whoops. Now, the value of a function is the y values. And so if you say the y values are increasing, then the function is increasing. So that's because f of x equals y. So they'll go through, yeah. Yeah. They also did the interval in inequality for each of those. So from -4 less than equal to x less than equal to -2, when actually it should be -4 less than x less than -2. And this would be from -2 less than equal to x. Oops. Because we're talking about the x values. That's why we're using the x here, not the y. less than equal to 0, when actually it should be written as -2 less than x less than 0. And then from 3 less than equal to x less than equal to 4, which should be 3 less than x less than 4. And then from 0 to 3, okay. Now they'll ask for one or the other. Sometimes they'll ask for both. When I ask it, I just ask it, and whether you want to write it as an inequality or as an interval, I don't, it's what you prefer to, how you prefer to write it. There are some professors who will want you to write it a specific way. There are some times where I require that, but not for this. Okay. Now, the definition for an increasing, decreasing, or constant function. If a function is increasing over an interval I for any choice of x of 1, x of 2 in that interval, where x of 1 is the smaller of the two values, then f of x of 1 is less than f of x of 2. That means as your x values increase, your y values increase for an increasing function. A function is decreasing on an interval I if for any choice of I of x of 1 and x of 2 in the interval, with x of 1 being the smaller value, you have f of x of 1 is greater than f of x of 2. So that what that one is saying is, as x increases, the y values decrease. So the value of the function is always going down. Now we say a function is increasing if it's increasing over its entire domain. Like x cubed is always increasing on its domain. The cube root of x is always increasing on its domain. Where x squared is not. Part of the domain on x squared, part of it you're going down, the other part you're going up. So it's not an increasing or decreasing function. Decreasing function is the same definition, except you're getting smaller, you're getting more and more negative. Where with increasing, you're always getting more and more positive. Okay. A constant function is where the y values are always the same. Any x on the interval will be the same number. F of x of any number on that interval will be the same number. And that's a nice little graphic of it. Well, I need to back up a second here and talk about why the parentheses are more appropriate than the brackets. At the brackets, it means it equals. It can be part of it. All right. Let's look at -2. -2 is where it switches from being constant to increasing. At -2, is the function still being constant? Yeah, because we don't know what's happening on the other side yet. On the other side of 2, it's still not being the same value. It changed, so it's no longer being constant here. This is a point of change. At a point of change, it's neither one or the other, because that's where it's transitioning. Here, it's like throwing a ball up in the air. When it hits its highest point, is it still going up? No. Is it coming down? No, it hasn't started that yet. So it's not doing either. So you're walking up a hill and you get to the top of the hill. Are you still ascending? No. Are you descending? No, I haven't started going down yet. So that's why parentheses are more appropriate here than the brackets. But for some reason, the author decided to use brackets in these definitions, which just flat out wrong. But that's my opinion. Now, when we talk about the local max and the local min, I will occasionally call these relative max and relative min, because that's a more formal definition, a more formal term than local. A function has a local maximum at C, so C is an X value, if there is an open interval that contains C. Okay, so C has to be inside an interval. It can't be on the endpoints, because in open interval, you don't include the endpoints. So it has to be inside here. So that for all of X in the open interval, f of X is less than or equal to C of X. So here I have C, and f of X takes it up to here, and all the other X values are below that or they equal it. Then in this interval, this is the maximum value. So you have one local maximum in that interval at a specific X value. Now it could be 2 X values in there, give you the same local maximum, but usually when we talk about local maximums, we want our interval only to include that high point. And so I have another local maximum over here, and it has the same, the high point is the same, but it's at a different X value. So we always talk about a local maximum at an X value, at C. So we have a local maximum at C, or a local minimum at C, so that it happens in both. But with local minimum, it's the smallest Y value in that interval. So it would be down here somewhere. Now, on the graph, when we start talking about this on a graph, right? So it looks something like this. That's what they have there. And if they don't put they should have put arrows on the end there. They did. Okay. So I look at my low points, I look at my high points. I look at the top of the hills and the bottom of the valleys. Those are where your local max or your local min are. The local maximums are at the top of the hill. The local minimums are at the bottom of the valley. So I can't say it more simply than that. And it has to be on a hill or in a valley. It can't be at the end. So sometimes you'll have something like this where they'll show something like this. All right. This point and this point are not local minimums because they're not inside an interval. Right? Remember that part of the definition of a local maximum and a local minimum is that they're in an interval. So it won't be an endpoint. Okay. But here we have two local minimums and one local maximum. All right, we have a local maximum. We have a local maximum of 3 at x equals 0. We have to state where the local maximum occurs, not just what it is. All right, the local maximum is the y value at the x value that gives it. Another way of stating this is a local maximum at f of 0 equals 3. The phrase here, or we say the local maximum occurs at the point 0, 3. In this case, we can say the local maximum because there's only one. And we have two local minimums. All right, we have a local minimum at the point -2, -1, and another local minimum at the point 1, 0. So the local minimum values are -1 and 0 at x equal to -2 and x equal 1, respectively. Is that making sense? Because we can't have a y value without an x value telling us what made it. So I just can't say 0. I just can't say 3. Because according to this graph, there are two number 3s here. I mean, there's 3 x values that give us 3. But which one gives us a local maximum? Right. I have 3 points here that have 0 as the y value. Which one gives us where that point where 0 is a local minimum? And this is the, well, with this graph, this is the only one that gives us a local minimum. But we still need to say -2 gives us -1. Now to find the intervals for where f is increasing and where it's decreasing. Okay, so well, yeah, as x goes this way, the y values are decreasing up to here, and that x value is -2. So from -infinity up to 2, it's decreasing. So that's how the textbook would show it. And then between here and here, the function is increasing as x goes that way. And so what that was -2 here, and this is 0. So from -2 to 0, we would say it's increasing in there. And then from 0 to 1, the function again is coming back down again. And so from the interval from 0 to 1, the function is decreasing again. So here it was decreasing. Here it was increasing. Here it's decreasing again. And then the last interval, which starts at 1 and goes to positive infinity, because the function continues to grow forever that way. So here again is going to be increasing. So the local maximum value is f of 0 equals 3, has a local maximum at x equal to 0. And notice it says, since for all x close to 0, we have f of x is less than or equal to 0, f of 0. So the local maximum value is, and MyLab asks you in different ways of how to respond to this question. And then it has a local minimum at x equal -2 and x equal, all right, so the original question says, at what x values do you have a local maximum? And at what y x values do you have a local minimum? And so they were asking for the x values that gave you those things. And so that's why they're answering it this way. And then they stated that the local minimum values are f of -2 equals -1 and f of 1 equals 0. And so the increasing was from -2 to 0 and 1 to infinity. It looks like OD, doesn't it? And then decreasing from -infinity to -2, and from 0 to 1. Again, using the incorrect symbols. Oh, okay. Saying x is greater than 1 or equal to it is the inequality for this interval. It starts at 1 and keeps getting bigger. Now, absolute maximum and absolute minimum don't need to be inside an interval. They could be at the endpoints. Okay. So the absolute maximum, they use u in this case, is where the absolute maximum is the highest y value the function obtains. If the function keeps going to infinity, then you don't have an absolute maximum. And same thing with absolute minimum. Absolute minimum is the smallest y value that the function can obtain. But if it goes to -infinity, it doesn't have an absolute minimum. So in this graph, we have this point is the highest y value the function obtains, and this point down here is the lowest y value the function obtains. So this point up here contains the absolute maximum, and this point down here contains the absolute minimum for all x inside the interval AB, the closed interval AB. So I will tell you that there are some questions on the exams I give you covering this particular section that look a little tricky, because sometimes you have an arrow going up and you kind of forget that, and you think this is an absolute maximum. It is not an absolute maximum because 4 is not the highest y value this function can obtain, because the function keeps going up as x goes negative. So we have other y values that are larger than 4. So this is not an absolute maximum. It has no absolute maximum. Okay. But this point, is that a closed dot or no? Oh, that looks like an open dot to me. So that means it doesn't reach that y value. That point does not exist for the function. If it did, then we would have an absolute minimum there. But because that point doesn't exist, we don't have an absolute minimum either. So this function has neither absolute maximum or an absolute minimum. And neither does it have an absolute maximum because there's no interval where you have the top of a hill. And for the local minimum, again, this point would contain a local minimum if it was part of the graph, but it is not. So this function has neither. It has no absolute minimum, no absolute maximum, no local minimum or local maximum. So looking at the domain here, we're not including the point, the point 0, 0 in the graph, which takes away our absolute minimum and our local minimum. All right, we use a less than precise definition for continuous function. Here, oh, and it doesn't say here. A continuous function, a function is continuous if you never have to lift up your pencil when you're drawing it. If you can trace it without lifting up your pen, then it's continuous. Okay. And if it's continuous over a closed interval, that means it can equal the endpoints. Then it will have an absolute maximum or an absolute, well, it will have both, an absolute maximum and an absolute minimum. Because the endpoints have to be part of it. In this case, the absolute maximum and the absolute minimum are the endpoints. But what if we had a graph where that wasn't the case? So we're coming from this point to this point. So right here, we have an absolute maximum, which is also a local maximum. At this point here, we have a local minimum. No, we have an absolute minimum, which is not, and this point is not a local minimum. But at this point over here, we have a local minimum, but it isn't an absolute minimum. So an absolute extreme could be a local extreme. But if the extreme is at the endpoints, then those aren't local, because local has to be inside the interval. Okay, and that's what the extreme value theorem is. Yeah, all the extreme value theorem is within certain parameters, you reach your highest and lowest values. In that interval, you have a high value and a low value. They can happen several times, so you get several high values that are the same high value for different x values, but you have to state that when x is 7, 8, and 12, we have an absolute maximum of 17. Or we have an absolute value of 17 at these x values. And then you list them. So, and that's all this is saying. So it's a useful tool in mathematics. And we use it in calculus, and we use it in other sciences as well. All right, so using the graphing utility to approximate the local max and min, you just type it into the calculator, and you set your window values to go from, so where you have, what does it say? I got my calculator. You window settings for x min. Whoa, what happened there? For min x, or x min, not min, you set that at -3, and then x max you set at +3, and you leave all the other settings alone, and then you look at what happens in there. Okay. So, oh, so it requires us first to determine the open interval I, and then the graphing utility will then approximate the maximum and minimum value in the interval. Using maximum, we find that the local maximum value is 5.63, and it occurs when x equals 1.67, rounding to 2 decimal places. So it'll give you a larger decimal number, and we'll look at the next slide. Will show these. And then using minimum, we find the local minimum value is 1, and that occurs at x equals 0. Okay. So you type the calculator, you type the function into the y equals to graph it. And then I don't remember how you do that part of it. It's been so long since I've used my graphing calculator to do these kinds of problems. So calculate. Oh, I need to do y equals. That is just, what is, oh, thank you. That was weird. Okay. So what was it? A -2 to x to the what? I'm gonna back up so I could see this. It's been so long since I've done this. That's why I'm doing it. The third power plus 5x squared plus 1. Kablooey. And then I end up with the same graph they have there. calculate? Yeah. In the TI graphing calculator, if you hit the calculate button, which is second trace, a window shows up and you can scroll down for maximum and minimum. And you got to give it boundaries to mess with. And so I got the same numbers they had gotten. Yeah. And so my screen looks exactly like their screen. And then you can do the same thing to find the minimum. And you want your left bound to be to the left of where the absolute minimum is, where the minimum is. And then the right bound, you want it to be on the right side of where that minimum is. So you can find that point. So that's how you use the calculator to do it, where it does all the work for you. What was the other question? Determine where the function is increasing and where it is decreasing. So where the X value occurs for those local minimums and maximums is where the dividing line between increasing and decreasing on a continuous curve. Okay, so here we had, we're going to say 1.67. So at 1.67 is where it changes direction. So from negative infinity to 1.67, no, wait a second. All right, at 0. Yeah. Because we get a point here that is this, because of the graphing in a graphing calculator, you're using discrete numbers to approximate the graph of continuous numbers. So at that minimum here is at 0, and the maximum over here is at 1.67. And so inside here is where it's increasing, and from negative infinity to 0, it's decreasing, and from 1.67 to infinity, so it's decreasing. So on these two intervals, it's decreasing, and between 0 and 1.67, it's increasing. And again, I used parentheses where they used brackets. So there's the increasing, and here's the decreasing. Since we're talking, since we have a restricted domain from -3 to +3, so we need to include those. That's still a 0 there. So instead of negative infinity, it's from -3, and instead of positive infinity, it's to +3. I forgot that part of it, because we restricted our domain from to -3 and +3. Okay. Average rate of change. Here's the formula for average rate of change. Does it look familiar? It should look awfully familiar. Instead of saying A and B, what if it's X sub 1 and B sub 1? Instead of F of A, it's Y sub 1. Instead of F of B, it's Y sub 2. How many of y'all are familiar with the delta notation? This is a Greek letter delta. Delta means change. That's, as a matter of fact, that's where the delta got its shape, and its name is because of a river delta has that shape to it. Well, it's loosely triangular. And I was a geology major in college, and we talked about fluvial deposits, and deltas are fluvial deposits. Fluvial deposits are deposits made by rivers and streams. And so that it's interesting. Okay, but it's been a long time and I've forgotten most of it. But it's a lot of fun. So the average rate of change. So we have this point here. This point is A, F of A. And this point over here is B, F of B. And the average rate of change is how we're looking at how much the Y changes versus how much the X changes. So the Y changes by F of B minus F of A being divided by B minus A. What does this remind you of? This distance here is F of B minus F of A, and this distance here is B minus A. These are the X values. So this is the change in the X values. That's what this means down here, the change in the X values. And this going this way is the change in the Y values. And that's what the delta Y means, the change in the Y values. If I did this, would that help you see what's going on here, what we're talking about?
Slope.
Slope. This is just the slope formula. That's all it is, slope formula. Now, granted, the function could look something like this, okay? And these are the 2 points I'm looking at. So we're talking about the average rate of change between these 2 points. It's not necessarily talking about what's happening inside the function. We're looking at 2 points in time. What's the average rate of change between this point and that point? Well, what's the slope of the tangent line? I mean, what's the slope of the line that contains the 2 points? And that's how we find it. Notice they say A and B can't be the same value, because then that means we're dividing by 0. So that's why we can't have A and B be the same. So here we have a function. And the function is f of x equals x squared plus 1. So we have 0 gives us 1, 1 gives us 2, 2 gives us 5. 2, 3, 4. What is it, 5? Yeah, 2 gives us 5. 3 would give us 10. So the graph of it, whoops, looks something like that. And so we want that. So what I'm going to do here, So we're going to look at two things. We're going to look at the average rate of change between these 2 points. You can barely see that line, right? Let me make it a little thicker. These 2 points and the average rate of change between these 2 points. So we're going from 0 to 2 and from 1 to 2. So A equals 0, B equals 2 in the first case, and in the second case, A equals 1 and B equals 2. So F of 0 equals 1, F of 2 equals 5,
So I believe we're on time.
oh, we're out of time. Oh, we're 3 minutes after. So we'll pick up with this next time. Thank you for reminding me
No
or
problem.
letting me know, because I would have gone on for another hour and a half or two before I realized. So if you have questions, go ahead and hang around and ask me any questions you may or may not have. Any comments you may or may not have, or if you just want to hang around and see what else other people are asking or saying. So otherwise, you're free to go, and I'll see you Thursday. And I've been telling my other classes that I'll see them on Wednesday, even though it's a Tuesday, Thursday class. I kind of got mixed up this morning at 8 o'clock, what day of the week it was. All right. There really isn't, homework really isn't due until the exam day. So you need to keep current with your homeworks. That's what I'm saying, is you need to keep current with your what's going on in class by what we're covering in class. Where did we, what was that slide we ended up on? Oh, dadgummit. 97. That's where we wind up, at 97. So I'm looking at what section we're in. We're in section, oh, we're still in section 1.1. We're not even done with section 1 yet. Oh yeah, we are. One, 3. So we've done 2 sections so far. And we're into the 3rd section. So you should be done with 2 sections and working on the 3rd one. And she's already left. Okay. So Angelina and Maria, do y'all have questions? Nope. Yes, maybe so. Okay.
So just to clarify, it's only sections 1 and 2, right, that are due?
You should be done with those.
Okay.
Or
Thank you, sir.
you should definitely be done with section 1. And if you're not done with section 2, you should be close to being done with it. Okay.
Okay.
But the due date, well, it's not actually a due date. It's a date that I will I will pull the grades off of it. Because you can continue working after the next exam, but I pull the grades to help with exam grades. So. But you should be working in it and staying current. And that's something I need y'all to be doing, is to stay current with the homework. So you should be done or almost done with the second homework assignment and ready to start the third homework assignment.
Okay.
All right.
All right. Thank you.
Okay. Take care.